Hello everyone, in this video we're going to be talking about differential mode noise in circuits, specifically in OpAmps. And I'm going to explain what it actually is and how it can be minimized. So right here you can see a design of an OpAmp, and how they are made is that at the input they have a very big resistance that we can say that's also infinite input resistance, so no current can enter here. So what we actually amplify here is not the current but the voltage, specifically the difference between those two inputs. So for example, if we have 2 volts up and 1 volt down, we will amplify the difference between them, which is 2 minus 1 volts. So now differential mode noise is the disturbance that is caused by an outside varying electromagnetic field or just a magnetic field. What it does is it will add, for example, 1 volt up, so here we'll have 2 volts plus 1 volt, we'll have 3 volts as our new thing, and here it can subtract, for example, 1 volt minus 1 volt, 0 volts. So now instead of amplifying our original thing, we will need to do the new thing, which is 3 minus 0, 3 volts. So like this, all our information is corrupted. We amplified something completely different, so of course we don't not want that. And now I'm gonna show you 2 ways to absolutely minimize this bad influence. Now the first one has to do with the physical distance, because as you can see over here there's a physical distance between those 2 cables, and based on Faraday's law, which states that the electromagnetic force is minus the derivative of the flux. Okay, I said B here because of a magnetic field, but it can also be an electromagnetic field, so I'll remove it. So this means if there is more area, this right here is the area that we're talking about. If there's more area, then that means that there will be more flux, and that means that more electromagnetic force will get created, which is basically our disturbance. And we'll call the electromagnetic force just in the induced voltage, because that's what it actually is at the end of the day. If you would like to watch a video also on Faraday's law and Lenz's law, where I explain how exactly the external field will influence the circuit, click on the top right on this video and get back to this video afterwards. So here the first fix that we can do is put these 2 cables as close as we can to each other, as close possible, so we minimize the distance, so we minimize this disturbance. But to go even further, we will use a very elegant trick, and what we will do is twist the 2 cables one over another, like I did right in the picture. Now, based on Faraday's laws, if there is a changing field, or in other words, if the flux is varying, let's say if a magnetic field is increasing, then another induced magnetic field will get created that will try to oppose that external magnetic field in order to get things back to equilibrium. So, for example, if we have an external field, I will put it in white, that's like this, that's trying to increase the flux. Some other fields will get created that are induced, and I will draw them in orange, so they oppose those white fields, so they try to get everything back into equilibrium. Okay, now listen closely, because this is a very important part that I'm gonna tell you right now. Since we previously said that here there's a big input resistance, and that means that no current can pass. That means that if there's no current, also no other electromagnetic fields will get created around it. So we won't actually have induced currents and magnetic fields. The only thing we will have is induced voltage. That is our actual disturbance. But the important part is that I still drew the induced currents and magnetic fields. That will be, in this case, if you do the right hand rule that I taught in the other video, the currents will go like this, okay? And the magnetic fields are already here, and I still drew them in order to understand the direction of the induced voltage. But remember, the currents and fields do not exist here. It's just a convenient way to prove to you that there was an induced voltage. After I understood this, I will delete the induced currents and magnetic fields so you don't get mixed up. And the important thing is that you just continue to focus on the induced voltages, because those are our actual disturbances and those are real. Now I will assign a plus 1 volt, a positive induced voltage on the ones that will push the current towards the right. So we will do plus 1, plus 1, plus 1 plus 1, and I will call -1 on the voltages that push current towards the left. -1, -1, -1. So now that we know the direction of the induced voltages, we can easily delete our currents and magnetic fields, which we do not need here. So now you can finally get why this twist is so important. Now, if you try to follow the orange line, for example, you would have +1 here, -1 down here, and then +1 again, and -1 again here. So that means that there were some currents some voltages that were trying to push current forward, some backward, and if you can see, this equals to 0, this equals to 0 when you sum them up, and it all cancels out perfect. The same goes with the green line, -1 plus 1, -1 plus 1. So also here, they all cancel out perfectly, and they all equal to 0. This means that we found an elegant way to stop the outside disturbance. So in that way, we were able to amplify whatever we were trying to amplify in the first place. I hope this gave you an in-detail explanation of what differential mode noise is and what to do to minimize the disturbance. I hope you liked this video. Like and subscribe if you did, and hope to see you in the next one.